Okay, so so this lecture is about development and robotics, or development and AI. So the basic idea is, what can we learn about how to train robots from what we know about how children grow up? That's the spirit. And this, okay, this slide is just always to remind you, but this is the slide I want to actually start with. Uh, this is a quote from Alan Turing's 1950 paper. I mean, this is a paper which is like, the title is "Can Machines Think?" and it proposed the so-called Turing test. But he has this beautiful line: instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So Turing in 1950 had this idea that the way to get to an artificial intelligence is to start with the brain of a baby. So this is kind of like your genetic capability. Basic genetic capability is like the prior that you build in. And then after that, you subject the child to some course of instruction. And then when the child becomes an adult, you've got your AI. Okay. And now Turing was writing this in 1950. And at that time, actually, what we knew about child development was rather limited. There had been some psychologists who had studied the problem. I mean, the most famous names are Piaget and Vygotsky. Write them down. Piaget, and he was a Swiss scientist, and then Vygotsky, and this guy was in the Soviet Union. So if you are curious about the early history of child development, read Piaget or Vygotsky. Piaget emphasized the development of children through various stages of capabilities. Vygotsky emphasized the social nature of learning, how we learn from the environment with peers and parents and caregivers and so forth. Okay, but we know now a lot more details about how children acquire their perceptual capabilities, their motor capabilities, and how they learn about the world. And there's so much to say here. I mean, I have a book here called Developmental Robotics, which is all about how this interplay between what we know from child development and we can try to use for robotics. And there are even conferences on this. There's a conference called ICDL, which is International Conference on Development and Learning, which is on this theme. Okay, so this area has existed for like about 25 years. People have had this idea that let's try to build robots in the same way that children learn. The devil is, of course, in the details. I mean, you can have this high-level idea, but how do you operationalize it? So with a child, I think if you look at the figure, you see some of the stuff on the left, which is this girl is in the crib and maybe she's playing with various things and she's tapping at various objects and so forth. So what's the kind of signal that she will be getting? She'll take some object, she'll put it into her mouth. So then there is the tactile signal from the mouth. There is obviously the various joints, the joint angles, the proprioceptive information. There's vision. There is audition, because when you hit some object on something, you have a sound. So it's a very multimodal input. And the child is playing. Now, in the course of this, so it's all self-directed. Now, there is this last stage when the child goes to the zoo and the mom says, "Oh, that's a zebra." But that is like this little tiny sliver of supervised learning. Most of the learning is essentially self-directed by the child. I wouldn't call it just unsupervised learning. I mean, you can use the term self-supervised learning, because part of it is actually reinforcement learning as well, because the child is performing actions and then observing the consequences of that. But the reinforcement learning or learning to act in the world is in fact more subtle than that, because the child is often not driven by very specific goals, but just goals to explore and play. And this is something we have been trying to capture in AI and robotics and not had very good luck, like the notion of what's called intrinsic motivation. Intrinsic motivation. And there's another related term, which is curiosity. So the child is interacting with the world to learn more about the world and build models. So the way to think of, I think the right way to think about it is as in my previous talk, which is that we acquire lots of models of the world, and the child's play is aimed at building models of the world. So when the child is sitting in the crib and she takes the bottle that the mom has just given her, and then the child throws that bottle, you should think of it as an experiment to learn about gravity, right? I mean, parents, of course, get very annoyed when the child does all these things, but the child is really doing all these experiments to build models of the world. Okay. There's a good philosophical statement here, which I want to do. This paper, I think, will be on your reading, this Smith and Gasser, because it's kind of a summary of the big findings from this child development literature. I mean, this literature is huge. I mean, up here, in fact, in this building on the psychology floor, we have colleagues here. We have 5 or 6 colleagues who've devoted their research careers to understanding how the process of child development. So there are thousands of papers and books, and I cannot possibly do justice in 1 hour. So I'm going to give you a projection of some of this to robotics. But there is in this paper, which says embodied cognition, 6 lessons from babies. So there's one point, which is this embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory motor activity. And then they've abstracted out six points, 6 lessons. So, and what I'm going to do is I'm going to give you examples of how you can take these principles, which come from like this paper written by psychologists, and how you can operationalize them and get value out of them in robotics. I thought that initially I had planned this lecture as giving you a review of the literature from developmental psychology, and I think that's going to be overwhelming and just too much. So I'll really try to do it from the point of view of some examples of how it's been useful in robotics. So be multimodal. So I already gave you something about that, right? So vision, touch, proprioception, etc. Be incremental. So we do not learn, we don't have like, oh, there are like 17 different skills, each of which you will learn end to end separately. That's not how it works. You acquire some skills, then on top of that, you build the next set of skills. On top of that, you build the next set of skills, and so forth. Be physical. All of these require interacting with the physical world. Exploration. So this is like explore in the same sense as in explore, exploit in the reinforcement learning world. Social here means learning from others. And then finally, language. So I'll give you some examples of this, but I'm going to start with one or two case studies, which for me were very influential, meaning that this is one of these classic debates that has occurred in AI for the last 70 years. There are some people who care about looking at natural intelligence and biology and psychology, and there are other people who don't care. And those people stand up and they usually always give this argument. Okay, airplanes don't fly like birds, therefore I do not care to know about birds. Go away, I don't want to learn anything about psychology or neuroscience. I mean, I've heard this argument like 17,000 times, okay? So, and maybe some of you are exactly from that school of thought. Sorry, I don't care. I believe in this, and I'm going to give you examples of what I have learned and how it has benefited my group's research in robotics. So here was one example, which was like in locomotion. So in locomotion, the standard belief is that animals have gaits, right? And here's a picture of gaits. And in fact, in my very first or second lecture, I told you about walking and running as two gaits that humans have. And this has been guiding the people in robotics forever. So starting from like Mark Rabert's work and including some of the learning work, that it starts by pre-programming a gait. So gait would be like the pattern of footfalls. So you program that in, and then you start after that. You build your controller based on that pre-programmed notion of gaits. Okay, and then what I was doing was I was reading some of this literature from the psychologists, and in particular, there is a psychologist called Karen Adolph. She is at New York University, she studies how children learn to walk. I mean, she studies many things, but how children learn to walk is a big thing. And the difference between how she studied children learning to walk and other people who've done this is she tried to study it in as natural a setting as possible. So she gives these kids who come into the lab lots of room so that they can walk in a much more free way and get a sense of how they actually learn as opposed to in a very, very constrained setting. And so she has a whole bunch of these findings, which you should read about. I think we'll put one of those papers on the reading list. For example, children fall a lot. Okay. So this is good because this tells you that maybe RLA is actually not a bad model. So children fall a lot. And whereas when people were designing robots, they say, oh, we cannot have the robot fall. Well, for physical robots, there's an issue, but I'll come to that. Children fall a lot, but it doesn't hurt them because they have soft bodies and they have low centers of gravity. So when they fall, they just get up and start walking again. So she has tried to collect data on how often they fall. So in 1 hour, they might have fallen like 100 times. So if you add it up over the course of how many, a child learning to walk, it's quite a bit. It may not be in the billions, but it is certainly, in the 1,000 to million category. Okay, so the trial and error is part of human learning. Okay, so I mean that's one observation. But the observation that I like the most, and to me was very influential, was this one. So here's this kid who's walking. Okay, so we are now, what are we looking for? We are looking for gaits, right? Either the walk gait or the run gait. Now let's see what actually happens. Okay, let me repeat. Okay, so this notation here stands for S means side, F means front, B means back. So this is like what kind of a step the child has taken. Okay. Side, front, back, right? Okay, where is that periodic gait going on for, forever? There is no gait here. What there are, so this is the slogan. Most walking bouts contain omnidirectional, not forward steps. So the child is not learning with like a pre-programmed gait from which the child starts and then is just fine-tuning the parameters of that. There isn't a gait to begin with. Now, a very important point to note here is that this is not necessarily true in all species. So we're talking here about human babies. This may not be true of a cockroach. So it may be that when a cockroach is born, the cockroach does have a gate pre-programmed through a through a CPG. Okay, that's totally possible. And because these other animals have much, much smaller brains, and they also don't have the time to afford to spend in learning. So like there are these pictures of these mountain goats. They're born and then pretty much they are able to walk, right? well, not true of human babies, right? When is our baby able to walk? There's more like 1 year old. Because we are, and there's a distinct, the people talk about this in psychology, the different kinds of species. These species which have where there is a long period of development where the child is essentially helpless and relying on the care of parents to take care of them for this extended period. And then they can afford to have this huge period of learning. And that gives them eventually much smarter brains. So species which have this long period of development, as opposed to being pre-programmed and ready to go on day one or R1 or second one, there's a distinction here. And this is true. I mean, humans are, of course, prime examples of that, right? I mean, till the age of 18, you're dependent on your parents. I don't know, maybe you're dependent till 40, whatever. But this is also true, by the way, among birds. So chickens, they are not relying on this period of development when they are relying on their parents. They're ready, but they have small brains. Crows, on the other hand, are much smarter, and they have a longer period of development where they're relying on the parent to take care of them because they are not able to function fully on their own. So again, this is a topic on which many papers have been written. Alison Gopnik, our colleague in psychology, has written papers on this theme. Okay, now I want to come to a concrete robotics example. So because of this, we decided when we built our walking robots, we are not going to pre-program in gates. So we are just going to pre-program in general principles like move forward, smooth movement, minimize energy, and those principles, but there was no pre-programmed gate. And the advantage of that was that when we trained our robots with different target speeds, so a target speed of 0.375 meters per second, then this kind of gate emerged. So what you see here are, right front, left front, right rear, left rear. So the solid part corresponds to when the foot is on the ground. And then this is the gate which emerges when you give it a higher target speed. And it turns out that these different gates are emergent. These were not pre-programmed. And all that was necessary was the principle that you minimize your energy consumption. So I think we got something cool out of this result. But the starting point was this observation from the child development literature that children do not have pre-programmed gates. They're sort of learning to take steps. So therefore, let's do learning all the way rather than pre-programmed in a gate. And that gave us actually this very nice result at the end. And then this can be tied to energy consumption and so on. So I picked this example, which to me or to our research group was very cool. Because of that philosophical commitment to looking at child development, we got a nice result for robotics. Okay, next point, multimodality. So multimodality just means different senses like vision, touch, hearing, and so on and so forth. And so we'll go into this in detail, but this is from Housley's work. And here, when you want to solve a hard rotation problem, so the task is rotating an object in the hand. It turns out that for simple tasks, you can do it by just proprioception. But when the task becomes hard, like rotating about different axes, then you get value out of using both vision and touch. And here you see this camera, which is providing vision information, and then there is touch information, which is shown in the images on the right. So here are examples of the task. Okay, so that just each row corresponds to rotation about different axes and the generalization across different objects. But the takeaway that I want you to have, because this is just one task, but I believe it's going to be true in multiple tasks, that when the task becomes more difficult, you need more sensing. And in this case, you need vision and touch. And this figure is the important one, which is that the rightmost column corresponds to the y-axis here is about how successful you are at the task and in terms of accumulating rotation reward. So the rightmost column is what you do if you have knowledge of the ground truth shape and position of the object, which in reality you are not going to have because you have to get that from sensing. And the leftmost column is where you just rely on proprioception. And then in the second and third one correspond to just having vision or just having touch. And then the fourth one is having vision and touch together. So vision and touch together give you as almost the same performance as having access to ground truth. So this is for a specific task of rotating an object in the hand. But my belief is that this pattern will hold good for different tasks. If the task is easy, proprioception will be enough. If the task is hard, you might need to have vision or touch or audition. I mean, and more the better. And it depends on the difficulty of the task. Now, certain tasks which are very popular in robotics is like pick and place. So in my mind, pick and place is an easy task. And in fact, in my previous talk, I already said to you, picking up an object does not require vision. It doesn't require vision in a continuous loop to pick up the object. You should use vision to look at the object, find where it is, get the 3D location, and then you should be able to release you have your trajectory and you execute it. And now you need, at the end, you need touch to fine tune your finger placement or whatever. But you do not need vision, except for the initial planning, right? You do not need it as a continuous feedback loop. You did need it as a continuous feedback loop in this task because it's a more subtle task. Okay, here's another example. Now, this is one which shows how multiple modalities help you because one modality can train the other modality. So in the AI and machine learning literature, there has been a lot of discussion of unsupervised learning or self-supervised learning or supervised learning or reinforcement learning. And this has gone on for like a decade. And the reason is that most of the early or big successes of AI have come from supervised learning. And supervised learning usually means you have an army of people somewhere that you pay them, $10 an hour, and then they're marking for every object. There's a chair, there's a dog, there's a cat, etc., etc. Right? And then you have this training set, and then you train your model. Now, this is not how humans learn. I gave you that example of that kid, right? The number of examples of zebra that a kid gets from his or her parents are very few. But the kid has got all this expertise based on interacting with the world and acting in the world. Okay, so this one was the following problem. Okay, so here we have this robot, and what we are trying to do is to calibrate its vision system. And we want to do it in a self-supervised way. So what is the advantage of vision? Again, connect back to the last lecture. Vision is a distance sense. Vision enables you to know about some aspect of the environment before you actually get there. So it gives you a lot of safety, right? Once you get there, you could fall into a ditch. Vision tells you in advance, if I continue in that direction, I'm going to fall into a ditch. That's the beauty of vision. So a few seconds earlier, from the safety of a safe position, you know what the consequences are, right? That's the advantage of vision. Okay, but how do we train this vision system? So it goes back to the example that we had in the first part of this lecture. How did Nima's vision system know how many steps to take, or the motor system? Somehow there must have been some calibration process. I mean, throughout your life, you are calibrating. So that's what we are trying to model in this experiment. So now the idea is that when the robot is standing on the stairs, then if you look at the feet of the robot and These are joints, links and joints. So presumably you know your own body. So therefore you can solve the forward kinematics problem or inverse kinematics problem. So by working out the geometry, you can actually figure out that the front foot is 6 inches above the where the rear foot is, right? You can see how mathematically that could be worked out just from the joint angles, which you know from proprioception, right? Okay. I want to use this as a training signal for my vision system, because my vision system doesn't know in advance where something is. So this is my vision system, which I want to calibrate using my proprioception system. So, so now think of when the robot is walking, and like, let's just view this problem. How much higher the height of my front feet relative to my back feet, which I can calculate from proprioception. So as I'm moving, I'm going to know this number, 6 inches, 7 inches, 12 inches, whatever, right? And that's what this curve is. It's going to move up and down in some way, right? You understand how we can get this curve. Okay. And now what we imagine is that we shift this back in time. Oh, sorry. What happened? I wanted to show this figure has got. Oh, good. Okay. So I can, let's say I can shift this curve. I can take whatever my proprioceptive system discovers, and I can shift this back in time by 2 seconds. And then what I can do is I can tell the vision system to make that prediction for 2 seconds in the future. So 2 seconds from now, my proprioception will know how much higher my front foot is over my rear foot. Okay, I have my image that I collected now. So I have the image collected at time t and the proprioceptive signal at time t plus 2. And I can try to take from the image at time t, predict the proprioceptive signal at time t plus 2. So this is self-supervision. I didn't need to send off this image somewhere for people to label this as a cat or a dog. It's all self-supervised. It is from the robot's own trajectory. And that's what we are showing here. So you take the shifted signal from proprioception, and now your vision data, which is some set of pixels, you make those pixels try to predict what the proprioceptive signal would be 2 seconds from now. So now your vision has become a forward predictor. Okay, which is what we need, because in walking, the benefit of vision is forward prediction. Okay. Now, what is important is that initially the robot has some policy with which it can walk, because there's a chicken and egg problem. So the thing here is you can walk even though clumsily when you are blind. So this robot doesn't have this sophisticated forward prediction, but it can walk and it collects this data. So it's got proprioceptive data, it's got vision data. Now you train the system, right? And this is what we're going to see here. So we actually think of it as days of training. So in the first day, the robot is not very good in terms of walking, but it's collecting this data of vision and proprioception. Now you use that to train this forward predictor. So the second day, it walks better. And then on the third day, it's really very smooth, because now the vision system has become good at doing this kind of forward prediction. Yeah.
In the first day, how is it able to go up the stairs
clumsily, but so it's not very effective. At some point, it just sort of falls down and so on. So we can walk blind, right? It's just not very well. You can have a policy which can walk blind. There's a standard trick for this, which you can acquire with reinforcement learning. It's what's called foot tapping. So you tap the foot against the step, and if it encounters a step, then next time you try slightly higher, then you try slightly higher until finally it clears the step. So that and that it discovers on its own. Yeah.
Yeah. So once you have like a vision model that can predict where like the joints will be in 2 seconds from now or something, what do you do with that? Because to me it seems like this information you already have.
No. So you need to have trained a policy which can exploit that information. So we train two policies in simulation. One which is a blind policy and one which is a cheating policy, which acts as if it has knowledge of what will be happening 2 seconds in the future. Now, this policy cannot actually be run in the real world, but it can be run in the real world once you have this vision system which can do this prediction. And I think, I don't know if this video will work, but this works. No, I think the video is broken. But we did this experiment where we took the vision system of the robot and rotated the camera. So this is something which will totally mess up the calibration. But what happens is that as the robot walks, it collects data in the right setting, and then it works. And this is something that psychologists had studied before. It's called the prism adaptation experiment, and it's done like the following. So imagine that I have my glasses, right? And I'm going to reach some object, and I can reach that. Now what you do is you put a prism in front of my eye, or let's say one eye shut, the other, I put a prism so that all the rays are deviated by 20 degrees. So then when I try to reach, I'll be off. I'll be off by 20 degrees. And I'll keep trying this, and I'll be very frustrated. But sooner or later, I'll figure this out, and my system will become correct. What's going on is this kind of adaptation. Okay, now you play another trick on me, which is now you remove the prism. And now suddenly you're going to be off again, and then you will recover. So you can find videos on this on YouTube if you look for it. It's called prism adaptation. There are versions of this. There's another version of it, which is, suppose you wear glasses which are upside down glasses. So they invert the image upside down. And can you learn to bike in that? And the answer is yes. And the person who actually showed this experiment was a psychologist at Berkeley. His name was Stratton, and he did these experiments like 100 years ago. And he mastered the trick of how to bike with inverting glasses. And then, of course, once you remove those glasses, then it becomes, you need to again unlearn that behavior. So our visual systems and motor systems are always adapting. And this, to me, is an amazing capability which would be nice to have in robotics, because then you become robust to errors. Like if one of the joints. So like when we are walking, we can have trouble with like a sprain an ankle. It doesn't mean that now you're kaput. You're still able to walk with a limp. And so this ability to constantly adapt is, to me, is a very useful thing to have. And if you can figure out sort of these adaptation procedures which are always running, right, then that would be great. Okay, incremental. Let me give you an example of incremental. So this is when we have a policy which we can train for walking. Then here what we do is, on top of that, we learn a different behavior, which is what's called pursuit evasion behavior. So this is the pursuit evasion behavior. So this dog is chasing this woman, okay? And she is, so you can think of it as like a fun hide and seek game or whatever, okay? So, but notice that she fools him, right? It, okay? So, So now you could imagine solving this by an end-to-end training problem where you try to train for this task, and it would probably not work, or it would take lots and lots of trials. It turns out that if you do it in a two-stage way, first you train a policy which can walk, but it has given a direction. So given any direction of movement and an ability, you should have an ability to translate and rotate, which you train first. And on top of that, now you learn the strategic behavior of how to catch somebody. And it turns out that there are various behaviors that you need. One is that you need to do this predictive thing, which is that you go not to where the person is, but where the person will be, right? And that should emerge. You shouldn't have to program that in. It should emerge because you are solving a reinforcement learning problem, and the reward is for catching the target. And in order to catch the target, the robot has to do this prediction. Other things which emerge are like seeking behavior. So if you don't see the target right now, then you should look around until you see the target. So that also emerges. It doesn't have to be built in. So this is an example of the value of incrementality, which is you learn some skill, then you learn another skill on top, and then you learn another skill on top, and so on. It's very rarely the case that we are learning tabula rasa. As we are children, we acquire a series of skills. So let me give you examples from manipulation. The skill that children acquire early is that of reaching. So when they are in their cribs, they're flailing about and they move their arms so that their hand can touch something. They get pleasure just from that touch. At that stage, their ability to form grasps is not there. They are not able to grasp the object or manipulate it, but they're just able to get their hand to the right location. Then later on, they start forming grasps, and the first set of grasps are these power grasps, and then after that you get precision grasps and so on. So, but there are some skills learned, and then there are other skills learned on top of that, and other skills learned on top of that. Okay, but that poses the following question. How do you decide what is that sequence of skills, right? What is that curriculum? And that to me is a mystery, because ideally I would like not to hand build that in. Okay, but maybe this is part of what you get from your genetics. So my theory on this, which may be false, is that there are only two things you need from genetics. One is the rewards structure, and the second is the curriculum. Everything else can be learned, but I have no way to prove this theory. Okay, and then these are just more fun examples of in Berkeley, this sort of chasing behavior. Okay, be physical, explore. Okay, let me give you an example of this. So this is a paper from long time ago. It's learning to poke by poking. Okay, let's give a demo of this. Okay, so what is the task here? This is not a prehensile task. It's a non-prehensile task. It's essentially that there is some object. You have a photo of the object. There's some camera looking at it. And you're given, there is some initial configuration of this object. And then there's some desired final configuration. And what you have to do is to just poke the object, or you can do multiple pokes until it reaches the final configuration. So it's a fairly trivial task. Just push it's pushing, but pushing from some start configuration to some desired end configuration. Okay. So how do you solve this problem? So the idea here is that learning to poke by poking, meaning that you're going to do little experiments like a child does, by which you build a model of, if I apply this force in this direction, then this happens. And what happens may vary depending on the object and so on and so forth. Okay, so how does the setup? So the setup is that we actually want to have a forward model and an inverse model. Actually, let me show you the next slide. So what's a forward model? So the forward model is, it's given an image, it's given some action. Okay, so the control action in terms of what force to apply. And these go through some neural network, and then it predicts what will be the end state. So if I poke the object at 27,31, it goes by this force, it goes to 45,76. something like that, right? You will have a set of observations which you will then use to train these neural networks. So that's a forward model. I mean, and this concept is an important one. And people in neuroscience have had this concept for like 30, 40 years, that we have a forward model of the consequences of our actions. Okay, what's an inverse model? Inverse model is, I have the initial configuration, I have the desired final configuration. Tell me what is the poke to apply. I mean, this is what you have to do to solve the task. The one in the bottom, the forward model, is basically what that Craig slide was about, that we have these models of the world. The inverse model is what enables you to actually do something to achieve a goal. And the setup there is basically that you have the images, you run them through some layers of the neural network, and then you predict the action. And then there is some detail about how we train these models. So we essentially train the forward and inverse model together. But I mean, this detail is not important. What's important here is that we do not do this in pixel space. And this point is worth noting because there is a whole industry of people who want to do video prediction, which has existed for, again, quite some time. And I think a little bit not very successful in my view. And in that whole line of work was often about predicting pixels. And okay, maybe now you can say, okay, something like, like these generation models are sort of doing something like that. But I fundamentally don't find that super interesting. To me, I want to do the predictions in this more abstracted space. This abstracted space where the object is in some location and it gets to some other location. And that's what we are after here. And this is not a general solution. This is not solving the problem just for poking, but the philosophy which it captures, which is that you have you perform some experiments in the world, use that to get data from which you build a forward model, and you're simultaneously building an inverse model. And then prediction can be done using the forward model. If you observe a video, you can do prediction from the forward model. If you are a robot and you need to solve the task of doing rearrangement, then you use the inverse model. Question? Or a location of the object or whatever. Yeah. And this is a whole area in itself, but I believe in more abstracted level predictions rather than pixels. But let's go back to, okay, the architecture here is not interesting. I mean, it's like just the Siamese net kind of architecture here. But this was the important philosophical point. Be physical, be explore. Collect trajectories which you can use for training your model. Okay, going back to my propaganda point, which is how we went down this path, or how Pulkit went down this path, was exactly because he was inspired looking at the child development literature. Okay. Be social. Okay, this is easy. Be social means learn from others. And so this is imitation learning. And I think at Berkeley, we've been doing this now for some time. This was, I think, the earliest paper, which is in collaboration with Sergey and Peter's group. And here, the idea was you have this guy doing cartwheels. We have YouTube videos of that. We use that for training the Atlas robot to do the same sequence. And now you have a dense reward, because at every frame, it's being done in a physics simulator, but in every frame you have a target of what's the desired pose. And you may not be able to achieve it because the dynamics of the Atlas robot and this guy may not be the same, but it'll try to do the best it can. And then, is it time? Okay, I have 5 minutes. That's fine. So humanoid locomotion. So we have various bits of work at Berkeley which are in the spirit. So we'll talk about this in detail later. But here, here's the good picture, which is that to make this humanoid walk, Ilya made use of trajectories which are from humans like walking in this kind of a video stream. So you can detect the human, 3D-fy the human, get their joint angles, transfer them to the humanoid. Now you've got a trajectory, and then this is training data. And the training data is used for sort of this next token prediction kind of task. And it turns out that you doing that enables you to generalize and learn faster. We'll do this later, but okay, just to enjoy this video. So I think now Ilya has videos which are of it going up and down steep streets. So those are even more interesting. Okay. Okay. Another example of learning from others is how we learn to perform various manipulation tasks. So here, let's say there is some, like there's probably like cleaning, some cooking operation or cleaning operation or whatever. And the idea is that we have trajectories of that. We have trajectories from YouTube videos. So what we want to do is to lift these to 3D by lifting the hand to 3D and the object to 3D. And then these become training data for manipulation skill. And we'll again talk about these things later, but because I'm going to run out of time. But the high level, we have like a series of lectures on visual imitation. But where it fits into this child development rubric is this is being social. This is learning from others. And a lot of our learning is like that. So think about when people learn to become a bike mechanic. I mean, they don't learn to be a bike mechanic by just reading books or by just blind experimentation on their own. They go work in a bike shop. And then the senior bike specialist who does something, who shows the operations. Now, I think that example actually illustrates a lot, because when you go and become an apprentice mechanic, you're actually not starting from zero. You have a whole bunch of manipulation skills already, which you acquired as a child growing up, doing various experiments, playing with toys and so on. And then at the age of 18, you go and become an apprenticeship in a bike shop, and you can learn very fast. So I think I'll skip this. This is about hand reconstruction. This is about object reconstruction. Again, we'll do these things in gory detail later, but I'll end here. Thanks.